Okay, let's get into chapter 16, which has to do with thermodynamics and equilibrium. So we've already done a little bit with thermodynamics. Thermodynamics is the study of the relationship between heat and other forms of energy in any kind of chemical or physical process. Again, we talked about it last semester. We talked about enthalpy, which is the delta H value, the heat of the reaction. And we knew that delta H was equal to the heat of reaction at constant pressure. So again, delta H was the heat of reaction. So now we're going to talk just a little bit more about some other thermodynamic topics. We're going to define enthalpy a little bit more. We're going to talk about some other quantities like entropy and some other things. All right, so we're going to start a little bit here with some definitions. We're going to talk about the laws of thermodynamics. We've already, again, touched on this back last semester, but we're going to extend it a little bit more. And first, what we're going to talk about is what is internal energy? Because in all systems, energy changes. And heat, which we've talked about in the past, is only just one type of energy. So again, we're going to expand a little bit. So what is internal energy? Internal energy, which is given the symbol U, is just the sum of the kinetic energy and the potential energies of a particular system. So what does that mean? Of course, we know kinetic means movement, potential means just that potential, sort of stored energy. So, for example, if we're looking at a system, the kinetic energy might include the motion of the electrons, the motion of the nuclei, the motion of the molecules within the solution or within the gas or whatever, so the movement of the molecules. And then the potential energy has to do with bonding. So there's energy attraction between atoms in bonds, but also attractions that we talked about just not too long ago, attractions between molecules in a system. All right, so internal energy is a state function, and we talked about state functions back in chapter 5 as well. It's one that depends only on the present state and not how it got there. So it's looking at what it was, what it is now, and what's the difference between those things. So again, back in chapter 5, we talked about altitude being another type of state function where when you're at the top of a mountain, you are at a particular altitude. It doesn't matter how you got there. The altitude that you are standing on doesn't change, whether you were dropped from a helicopter or walked straight up the mountain, or if you went round and round and round. The altitude is independent of that. So internal energy is the same thing. It doesn't matter how you got there. And we've talked in past chapters like Hess's law, where you can do things in short, small steps or all together, and they should add up to the same amount. So it's the same here. So it's hard to know exactly what the internal energy is, but we can still measure changes in internal energy. What is it now versus what was it? How is it different from what it was? And so just like all kinds of changes in energy, we can say that the change in internal energy is the internal energy of the final minus the internal energy of the initial. So where did we start and where are we finishing it? Now, if delta U is a positive number, that means final is higher than initial, which means we've had to put energy in to get to the final energy, and so that's energy is gained. If delta U is negative, that means the system has lost energy because it's had to give off some. So like I said, back in chapter 5, we talked about one type of change in energy, which has to do with changes in heat energy specifically. And we also talked back then about how chemical changes can also cause work to be done. So what does that mean? What kind of work can be done? Well, it can be electrical work, nuclear work, or mechanical work, which is what we're going to focus on here. So internal energy, changes in internal energy is just the changes happen because of exchanges of energy between the system and surroundings. Either we gain energy from the system gain energy into the system from the surroundings, or lose energy from the system into the surroundings. So, and the type of energy that we're going to focus on is heat and work. So heat, as we've already discussed before, heat is the energy that moves into or out of a system because of a temperature difference. So we know that your coffee cup gets cooler over time because if it's hot, eventually it transfers some of that heat to its surroundings and loses that heat. And so heat is just movement, is the movement of energy in terms of temperature differences. And then work is an energy exchange that has to do with movement of objects. So the literal definition is that work is when we move an object with a force of F through a particular distance. So work is equal to force times distance. So I think this picture can help us see a little bit. So here's a system where there's a gas inside the cylinder and it's free to move, which means that it's open. It's kind of open to the pressure, the atmospheric pressure, because it's the weight can move up and down, the piston can move up and down. So what happens if you heat the gas? Well, in the instantaneous time, the pressure builds, because if you heat it up, the gases start moving faster. Because the pressure is constant, because it's open to the surroundings, the volume is going to increase because to keep pressure constant. And so what's going to happen is that piston is going to move up, right? So we heat it. So two things are happening. We're heating the gas, so the system is gaining energy by heat, absorbing heat, but it also loses energy via work. What that means is the piston moves up, and so the system is doing work on the surroundings, and so it's losing work. So that movement of the piston is a type of work. So just keep in mind some of the sign conventions. If work is done by the system onto the surroundings, which is what that was a case of, work is negative because the system is losing work to the surroundings. If work is done on the system, then work is positive. So if that piston was coming down, that would be doing work on the system. We already know this. If heat is given off by the system, then we know delta H is negative. Or Q, sometimes we talk about heat being Q. Q is negative, and heat being absorbed by the system is positive. All right, so the first law of thermodynamics is the law of conservation of energy, which just states energy is neither created nor destroyed. So if we apply this to chemical systems, then we say, okay, the overall energy change of the system, it doesn't just disappear. It's going to be exchanged either by heat or by work, or the combination of the two. So the change in energy is from the heat of the reaction and the work done by or to the system. So when a reaction is run in an open vessel, like what we just saw a minute ago, that means pressure is constant. So anytime a gas is produced, then work is done by the system onto the surroundings. Work is negative. So it's expansion work. This is like we saw in the piston's moving. So if gases are produced, the piston will go up and work is done. And I think in a minute we'll see some other pictures where it'll make a little more sense. So, so if we replace the constant pressure of the atmosphere with a piston, so like we saw in that last picture with a weight, and if you allow it to move, that keeps it at constant pressure. And then we can see that work is being done because the gas is lifting the piston. So this type of work is called pressure volume work or PV work. It's really the only work we're going to consider. There's probably other kinds of work, but we're just looking at the chemical system, so we're really just going to focus on pressure volume work. So here's just another example. This is a reaction that we did back in the first semester. So we reacted zinc and hydrochloric acid. Well, when we did it in lab, we sort of did. We were testing the gas, so we kind of had a lid on the gas to collect it, but it wasn't a piston, so it wasn't quite the same thing. So in our case, when we did it in class, the system, it was just kind of open to the pressure, and so there wasn't any work being done, or at least we couldn't collect the work because we didn't have it set up that way. But let's say we did the reaction here, like you can see in a piston. Let me get my pen working here, and then we can. So here we have the reaction going on inside here. So this is zinc and hydrochloric acid. Well, there's actually two things happening. You may or may not have noticed when we did this reaction, but heat is actually being given off because the reaction is exothermic. So heat is being given off. And because gas is being produced, originally there was no gas, and now as the reaction proceeds, this gas is being produced in here. So what does that do? The piston moves up. That is a type of pressure volume work. So not only is heat being released, work is being done, work is being lost also because it's doing work on the surroundings. So work is being lost. So, so if the reaction is run at constant pressure, like we said, then the gases produced will represent a change in volume. So that piston goes up, so the volume increases. And so it's distance where the force is exerted, the gas is pushing up, and it's over a distance, and so that's volume. So the work that's being done is pressure volume work. So the pressure is constant, whatever it happens to be. Let's get a different color here. Pressure, whatever it happens to be, and then the change in volume, so that's how much did the piston go up or down. And so we're defining the work done by the system as pressure volume work. It's negative because it's going up, and so the work in this case, if it's negative, it's being given off by the system. If delta V is getting bigger, if delta V is getting smaller, then this number becomes positive, and so work's being done into the system. So it's just negative because the pressure, the volume is going up. So we can calculate the work being done by a chemical reaction just by taking the atmospheric pressure and finding the change in volume. All right, we're going to look at a little bit of an example. Now, let me just warn you right straight out, I'm not going to ask you to do one of these calculations because you kind of have to know units and what units are equal to, and we hadn't really gone over them, but I'm going to try my best here. So let's say we're reacting, so here we're reacting 1 mole of zinc, and we're reacting with excess hydrochloric acid, so that means all the zinc reacts, so it's the limiting reactant. And because it's a 1-to-1 ratio, 1 mole of zinc gives me 1 mole of hydrogen. I know that 1 mole of hydrogen is produced. And we can find the delta H for that reaction, or the heat of the reaction at constant pressure it's exothermic, and so it's negative 153.9 kilojoules for every mole of zinc reacted. Now they're giving you some information, and so we know that we looked at from the past slide. We know that the piston is moving. So this is my delta volume, my change in volume. So they're telling us here in this reaction that the amount of hydrogen that, because it's 1 mole of hydrogen, it's 1 atmosphere, it's 24.5 liters. So that's the volume of 1 liter at 1 atmosphere. I'm sorry, 1 mole at 1 atmosphere. So a liter, remember, is decimeters cubed. We can convert it to the units. What they're doing here is they're converting it to meters cubed. The units meters cubed. Remember that 1 liter equals a decimeter cubed. Or we mostly know that 1 milliliter is a centimeter cubed. So anyway, by converting 24.5 decimeters cubed to meters cubed, we get this volume. So this is the volume, or the delta V, the change in volume that the piston has gone through. And because we're at 1 atmosphere pressure, so that's our constant pressure. Now, what they did here is they converted it to a different unit of pressure, which is called the Pascal. And the reason why they did it is because of the units. We want the units to try to cancel. Pascal has the unit Newton, which we've never used before, per meter squared. That's what Pascal is. So here, if we have Newton per meter squared, and then we're multiplying it, so that's the pressure, and then we're multiplying it by the volume times meters cubed, then the 2 meters square will cancel, and we'll have Newton times meter. Well, a Newton times a meter, which I'm sure you don't know, is a joule. So that's how why this calculation is done this way. So if we figure out the work done by the system, then it's negative P delta V. And so that's 2.47 times 10 to the third joules, which is negative 2.47 kilojoules. So this is equal to the work. This is equal to the heat, Q. And so actually the change in energy, the total change in energy, is the sum of both the heat and the work. So the change in internal energy is the sum of the heat plus the work. The heat, negative 153.9 kilojoules, and the work, because it was done by the system on the surroundings, and delta V was positive, so it's negative as well. So the total internal energy change is negative 156.7. Most of it by heat, right? Most of it is the heat of the reaction, but a little bit of the energy change has to do with this work. So when this reaction occurs, the internal energy changes. Both kinetic and potential energies change, and most of it is heat, but partially some of it's work. Now, if we didn't have the piston there, we wouldn't be able to collect that work, but it's there just the same. Again, I'm not going to have you do one of these type of calculations. I'm just trying to work through the problem. All right. So, like I said, we already talked in chapter 5 about the heat of the reaction. So the heat of the reaction we defined as delta H. Heat of reaction at constant pressure is delta H, or the enthalpy of reaction. And so now we can define enthalpy as the internal energy plus any PV work. Because remember, let's see what this is. Since internal energy is equal to Q plus W, if we rearrange this equation, Q equals U minus W, and since W equals negative P delta V, then the negatives cancel out, and so that's why, so let's see, I think we've got it there. Right, so Q equals H, because it's at constant pressure, and work equals negative PV, and so you can think of it as delta. The delta's missing, but we'll just, it's P delta V. And so if you rearrange the equation, since U equals H minus PV, rearrange it, and we have H equals U plus PV. So because U, P, and V are all state functions, that means H is also a state function. We already talked about H being a state function. That means it only depends on the start and finish values and not on the pathway. And so that's why we were able to develop Hess's law, where we could say the heat of a reaction of two reactions that add up to a third reaction, the heats will also add up to the heat of that third reaction. And so anyway, delta H is the heat at constant pressure. So at a given temperature and pressure, a given amount of substance will have a definite enthalpy. And you may remember we were able to look up those values in a table, Appendix C, I think it is. So if you know the enthalpies of substance, then you can calculate the change in enthalpy for any reaction. So back in chapter 5, when we discussed delta H, we defined delta H as the heat of the reaction at constant pressure. And the standard enthalpy change for any reaction then, and you hopefully remember doing this, is the sum of all of the delta H of formation for the products. The delta H of formation, the little circle means standard state. Delta H of formation were the values that you look up at the back of the book in Appendix G. I might have said C a minute ago, but it's G, Appendix G. Those are the values that have been tabulated. What's the heat of formation of that chemical from its elements? You can look those numbers up. You multiply it by the coefficient, add all the products together. So that's the sum. And then find all the delta H of formation for the reactants, multiply times their coefficient and add them together. And then you take the sum of the products minus the sum of the reactants, and you get the delta H of the reaction. Again, the little circle just means standard state, which is the only state that we're dealing with. So if delta H is positive, that means the reaction's endothermic. That means that the heat of the products, the sum of the products, is greater than the sum of the reactants. So the delta H is a positive number. And if delta H is negative, that means the heat of the reactants are bigger than the products. So that's where we get the negative number, and that's an exothermic reaction. So again, those are numbers that you may want to go back in chapter 5 and look and see an example. I'm going to do an example in a little while of different terms, but you may want to go back and review what we did in chapter 5 with an example problem, finding the delta H for a reaction by summing the products minus the reactants. Okay, so like I said, we measure certain heats of reaction and use them to tabulate. So these are the delta H's of formation that I was just talking about, and you can find them in Appendix G. If they're on a test, you'll be given these values on a test, or if you're working homework problems or anything else, they're in the textbook in Appendix G. Okay, so now we're going to move on from enthalpy, and we're going to talk about a couple of other thermodynamic terms. So entropy is the next one that we're going to talk about, and spontaneous processes. So, you know, if I said to you, oh, if I put some water in a freezer and the temperature in the freezer is -10 Celsius, will the water freeze? Yeah, you'd say, yep, it'll freeze. And so I would call that a spontaneous process. That will just happen. It will happen. There's nothing stopping it. If I light a match and put the match to a bowl of alcohol, will it burn? Yes, it will burn. It's a spontaneous process. So we're going to talk about spontaneous processes. Some other examples: a rock at the top of the hill. Now again, and I'm not talking about the little initial push. So like I'm not talking about the match, that the fact that I had to light the match, but the point that if I put the match to the alcohol, will it burn? Yes. If a rock is at the top of the hill and is loose, will it roll down the hill? Yes. It will not roll back up the hill, but it will roll down the hill. Again, heat flows from a hot object to a cold one. So will that ice freeze? Yes, because the heat from the water will go into the freezer, and the water will get colder and it will freeze. So that's spontaneous. If I have some kind of iron object that's just sitting out in the moist air, it will rust. So some of these are quicker things. Some of these are much slower. I mean, you could sit all day and watch nail and probably not see it rust, but if you look at it maybe a year or two later, you're going to find it. So we're not talking about how long it takes, we're just talking about the process. So these are all processes that without requiring outside force will continue until equilibrium is reached. So spontaneous process, rock going down the hill. A rock just on its own going up a hill is not spontaneous. And again, just to mention again, it's important not to confuse spontaneous with fast. So like I said, a nail is going to rust in the proper conditions. You may not see it happen, but it's still spontaneous. It will happen. So speed is not necessarily connected. Now, there are two kinds of processes, and I think we could get really into the weeds with this, but we're just going to kind of stay on the surface. A reversible process is something that can be restored by reversing the change. So we think about our water. So if we put the water into the freezer and freeze it, can we unfreeze it? Yes, we take the ice cube out of the freezer and it will melt. So that's a reversible process. So phase changes tend to be reversible. An irreversible process then is one that can't be restored simply by reversing conditions. It has to take a different pathway to get back. So can a rock go back up a hill? Yes, but you're going to have to pick it up and put it up at the top of the hill. Can you heat a house when it's -5 degrees outside or close to that, which is, I'm recording this on that day where it's really, really cold outside? Yes, you can, but you're going to have to do work or put energy in of a different kind to make that happen. So that's irreversible. It won't just spontaneously happen. So many, we'll get into this in a little while, but many spontaneous processes will proceed with a decrease in energy, meaning they're going to give off energy. Delta U will be negative. It's going to give off. But just keep this in mind, and it's kind of where we're heading in this chapter. It's not necessarily true. Some spontaneous processes are endothermic. So remember, we talked about heat of reaction, and heat of reaction is a really important change in energy, but it's not the only change in energy, as we just saw. Work is a type of energy, and so that's why we're defining more things, because it's not always true. So, all right, let me ask you this. Which of these is spontaneous at room temperature and at standard pressure? Solid water becoming liquid, or liquid water becoming solid? We're at room temperature, so yeah, that's important to know. Room temperature, so about 25 degrees Celsius. So that's above the freezing point. So if you have liquid water sitting in room temperature, it is not going to spontaneously freeze. However, if you have solid ice sitting in a room temperature, 25 degrees Celsius, it will melt. So here's just an example, but think about that. Melting ice, you have to put heat in to melt ice. So it's positive, it's endothermic. However, this is the one that is more spontaneous, even though it's endothermic. So this is just explaining this this example up here. Many spontaneous processes are exothermic, but not all of them. And this is an important one right here. Water, ice melting at room temperature is actually endothermic, but it is spontaneous. So we'll see why later on. Systems in equilibrium are necessarily reversible. So if a system's in equilibrium, reactions and products are reversible changed. In a spontaneous process, the path between reactions and products is irreversible, and so equilibrium is not the same as a spontaneous process. If something's in equilibrium, it just kind of hangs out in equilibrium. So if we look at a reaction, we say, okay, will this reaction go in the direction that it's written? What we're asking is this spontaneous? And so the first law of thermodynamics doesn't answer this question. So the first law, again, just means energy is conserved. Well, that doesn't really tell us much about will a reaction be spontaneous or not. So let's look at some other situations. So what's going to happen? Here we have, a bunch of gas. I got to change the color of my pen. So we've got a bunch of gas here. What's going to happen when I open this piston? Well, as you can imagine, these gas molecules, because of just randomness, they're going to start making their way into the empty container, right? And so eventually what you're going to have is the pressure, the gas molecules will be about the same in both sides of it. So that is a spontaneous process. The gas molecules are spreading out. Will these gas molecules, will the reverse be spontaneous? No, these molecules, once they're already scattered out, they're not going to all move back into one side of the container spontaneously. You can get them over there, but again, you're going to have to force them to get over there by pushing them or doing something else. So, and actually, in this case, if this is an ideal gas, this process results in no change in energy. So this is a process that's spontaneous, but it doesn't really have anything to do with energy. And we've talked before about temperatures. Again, if we have this block over here is hot and Y is cold. Now, if they're not in contact with each other, they're really not going to transfer energy. But once we put them in contact with each other, heat will spontaneously flow from the hot one to the colder object. But overall, there's no change in energy because the amount is just heat going from one to the other, and so there's no overall change in energy. But this is still a spontaneous process because this heat is moving.